All right, we're going to compute a surface area of revolution. The curve that we started with is y equals 7x, and we revolved it around the x-axis. And so I've already drawn into the picture a little ribbon of surface, and the length of, or the thickness, the length of this little segment right here is ds, a small section of arc. So remember how we write that down. ds is the square root of 1 plus f prime of x all squared dx. So we're going to have to get f prime of x, and we might as well do it right now. So that's y prime for this y. Square root of x is just x to the 1/2, and I use the power rule on that. So I get 7 times 1/2 x to the negative 1/2, which cleans up nicely as 7 over 2 square root of x. So I think I'll go ahead and plug that into ds a little bit later. The other part that I need on this ribbon is the radius. So this ribbon is located at some horizontal value of x. The y coordinate corresponding to that is 7 root x. So there's my radius. And then I'm going to slice and unroll this ribbon. So I get this long, skinny, approximately rectangular thing. The thickness is ds. The length of it is 2 pi times the radius of the original ribbon that we unrolled. We could clean that up and call it 14 pi root x. So now I'm ready to write down an expression for the differential contribution to the area. We call that dA. And it's just the area of a rectangle. I get 14 pi root x ds. Plug in our ds from over here, including the f prime over here. And I get 14 pi root x times the square root of 1 plus f prime, that's this thing, squared. So I'm going to go ahead and square it while I'm at it. So I get 49 in the numerator and then 4 in the denominator. And then square root of x squared is just x dx. And we'll just clean this up a little. I'm going to distribute the root x into the interior of that square root. That just puts an x into the interior. And I end up with x plus, well, the x's cancel in this term, x plus 49/4. Now that we have an expression for dA entirely in terms of one variable, I use an integral to add up all the area contributions, plug in the expression for dA, and then I'll start, something I forgot to write here is that this interval was 2 to 4.6. So I'll start at 2, end at 4.6, and I get 14 pi square root x plus 49/4 dx. Now nothing special has to be done to perform this integral. I have a function of x in here, but the derivative of it is 1, so the chain rule backwards is not necessary. So this is just this expression to the 1/2 power. It might be good to look at it that way. So I get 14 pi x plus 49/4 to the 1/2 dx. Then I just use the power rule on this, so I add 1 to the exponent and divide by the result. So that gives me 3/2 for the exponent. Dividing by 3/2 is the same as multiplying by 2/3. So let's do all that in the next step. So I have, maybe I'll just move constants out in front. I have 14 pi times 2/3, and then I have x plus 49/4 to the 3/2 evaluated from 2 to 4.6, and we're about to wrap it up. I have 28 pi over 3 times 4.6 plus 49/4 to the 3 halves minus 2 plus 49/4 to the 3 halves. And now it's time to just plug that into a calculator. And when I did this, I got approximately 128. Oh, excuse me. Let's see if I can. I should redo it. I was remembering a different calculation. So excuse me while I type for a while. So I have 4.6 plus 49/4, 3 halves, and then minus. Right, so I got 450.8 approximately. The units on that are just square units for whatever units these represent. In a calculus class, these usually aren't labeled as like inches or centimeters or something, so it's okay to leave it without units on your final answer.